Welcome back after the break. I hope you enjoy your break. Okay, that's the material we discussed with you 2 weeks ago. We started with you discussing spectral properties of matrices and linear maps. I will quickly remind you what was that about. So this is the first slide we discussed with you on Thursday 2 weeks ago. I call it spectral analysis and definitions. So here we go again. We introduced with you the idea of eigenvalue. That's the number which is associated with the matrix, and it is associated with the matrix in the following way. A number called eigenvalue for the matrix A, if you can produce a vector, non-zero vector, n-tuple, non-zero n-tuple, which works like this, which connects your matrix and your number through this identity. If you have such a vector, then that number is called eigenvalue, and the vector which makes this identity work, you call this vector eigenvector. Okay? That was the beginning of it. I showed you a few examples where this connection appear. Then we moved on, and I showed you the main tool which helps you to look for those. For these numbers, for these eigenvalues. This is a tool which is called characteristic polynomial. It was my next slide on Thursday, 2 weeks ago. It was this slide. Yeah, this is the one. So effectively, this is the result which I called theorem 2 weeks ago. Here it is. This is the one which is the main tool you're going to use to find these eigenvalues. It says this. It says this: any eigenvalue of a matrix is always solution to the equation like this, and vice versa. Any solution to the equation like this is an eigenvalue. So all you need to do now, you need to write up this equation, which turns out to be a polynomial of a degree. Degree of that polynomial will be the same as the size of the matrix underlying this characteristic polynomial, and you need to solve that. Solving a polynomial is not an easy task, but one way or another, the whole business is reduced to just a technical process of solving a polynomial. Okay, so it's the main tool you have in your toolbox when you do spectral analysis, when you look for eigenvalues of a matrix. You write up this characteristic polynomial, which is of this shape, and you attempt to solve this polynomial Every solution you find, it will be an eigenvalue for your matrix. Not only actually, with the eigenvalues, you also look for the eigenvectors. For those two, or for the eigenvectors, when you look for the eigenvectors, you need to solve some system of linear equations. That's again something I showed you 2 weeks ago. I'll show you a few examples today to refresh your memories on the way we do it. Okay, let's just look at the example. I forgot my printout. Let's just do one of the examples. I'll choose a map with some geometrical background, the map which we discussed with you a few weeks ago when we discussed with you linear maps of every possible sort. Projection map, if you remember. Let's just do analysis for projection map. So, it's a bit small. Let me just open this. I'll zoom it in. Okay, so projection map, we met this map already. We met this map when we discussed with you matrices of linear maps. Now we're going to study this map from the spectral point of view. So the map itself, it's the one which works like this, between n-tuple and n-tuple, real numbers for now. We have a direct formula for the map. That's a direct formula for the projection map. This is a direct formula for the projection map. Okay. Like I said, when you go for the eigenvalues, even if you're discussing linear maps in abstract setting, like this is the one, when you discuss linear maps, first you have to identify metrics of that linear map, Back when we discussed with you projection, we did one example with you. I chose a specific dimension, 3. I made a numerical choice like this. And back then we discovered with you that if you take standard basis, E1, E2, E3, if you take standard basis, the matrix of this map with respect to the standard basis, that's notation we used to have for that, matrix of a linear map with respect to a couple of bases. In this case, we take standard basis. The matrix of that map is like this. This is something we've done a while ago. If you look through my uploads or through your notes, you'll find this. Or you can try to recover the same computations once over again later on when you revisit this slide. That's my beginning of the spectral analysis. So once again, that's the point which I made on Thursday before the break, and it's the point which I make here again. You can introduce, even though originally when you introduce eigenvalues, you do it for maps, you can introduce eigenvalues for linear, I'm sorry, I misspoke. Originally, when you introduce eigenvalues, you do it for matrices. I said maps, I meant matrices. You can do it for maps via this structure, via first building the matrix of a linear map with respect to some basis, and then finding the eigenvalues of that matrix. Okay, so we have this matrix. Let's just try to go through the process of identifying the eigenvalues and eigenvectors. First, I need to build the characteristic polynomial. Here it is. This is the characteristic polynomial of my matrix, right here. I need to actually find this polynomial, actual numbers in there. So here it is. Matrix A take lambda I3. I3 is the identity of size 3, is this matrix. Yeah, it is this matrix. I put here 5 lambda because when you subtract lambda times identity, because of this 1 and 5, because of this 1 and 5, if you bring everything to the common denominator, the actual expression will be 5 lambda. So, in fact, for convenience, I'll make a substitution like this. If I make such a substitution for the convenience purposes only, then my matrix, this matrix will take this shape. My matrix will take this shape, and I will find my characteristic polynomial, this polynomial, PA lambda, in terms of mu rather than lambda. It will take a bit simpler form if you do it in terms of mu. So here it is. My characteristic polynomial. What do I do? Okay. I need to evaluate this determinant. This factor in front, it's simply 1 on 5 cubed, right? When you multiply a matrix by a number, the associated determinant is multiplied by the power of that number, and the power is actually the dimension of the matrix. That's why this 1 on 5 in front of the matrix, it goes into 1 on 5 cube in front of the determinant. Now, when you go for the determinant, you make the observation that you have these lots of zeros present. So if you take this cross as the basis of your evaluation, then you will have the factor negative mu, here it is, and then there will be minor, which consists of these 4 elements. You will have a smaller determinant, which consists of these 4 elements. Do I have the value for that? I do actually, here it is. So this is a product of this 1 take mu times 4 take mu, and minus 2 times 2, which is 4. This is a complete evaluation of my 3 by 3 determinant. It is so easy because of abundance of zeros in that determinant. So here's my characteristic polynomial in terms of mu, but still it's a characteristic polynomial, which if I expand the expression in the brackets here, it becomes like this. It's very easy to factorize. It's partially factorized already because we have this mu already factored. So if I well, I don't have to factorize much. I just have to say that my roots are, one of them is 0, the other one is 5. Back on Thursday, a week ago, in association with eigenvalues, I introduced the concept of multiplicity. Multiplicity is something which sounds a lot like multiplicities of roots for polynomials. It's close. So in terms of this polynomial, the value 0 has multiplicity 2, isn't it? Because you have one factor mu here, the other factor is hidden in this bracket. So this multiplicity 2 of root 0 in this polynomial, when you transform this terminology to eigenvalues, eigenvectors universe, you say that the eigenvalue 0, it is 0. I mean, even if you do back substitution here, because you have to come back to lambda terms rather than mu terms, this eigenvalue 0 has algebraic multiplicity 2. So here's my back substitution, lambda 0, lambda 1. This one has algebraic multiplicity 2, because we have two factors here. The other value, lambda equal 1, which corresponds to the value mu equal 5, it has algebraic multiplicity 1. Algebraic multiplicity here 2. Oh, that was a mistake. Algebraic multiplicity here is 1. Okay, so that's how you find the eigenvalues, something we will discuss with you on Thursday before the break. Now we need to find the associated eigenvectors. That's what you do for that. Look at this. So first you do it for each of the eigenvalues individually. So I take the value lambda equal 1 from here. I take the value lambda equal 1 from here. I need to find those vectors which make the identity work. So what I do, I just build this matrix with my particular choice for lambda. 1 is a matrix with 1 across here for lambda, so it's negative 4. It's negative 4. Sorry. 0, 0, 0, 2, 0, negative 1. We need to find the vectors in the null space of this matrix, or actually we can find the whole null space for this matrix. When you go after the null space, you need to do row echelon form transformations. As before, I have pre-computed values on this slide. I have pre-computed values on this slide. The row echelon form of this matrix is this matrix. You can see one non-leading column, which makes you think that which actually confirms that this matrix will have one-dimensional null space. The dimension of the null space is something which we call geometric multiplicity of the associated eigenvalue. So this value 1, which had originally algebraic multiplicity 1, it also has geometric multiplicity 1 as well. It's just the reason for that, the null space of this matrix is one-dimensional. It's only one non-leading column in this matrix. We still need to describe the null space in full terms. So we need to find the solution to this to this system. I do it a bit down here. Look at this. So what I need to do, I need to parameterize the unknown associated with the non-leading column. Here's my parameterization. Let's just say T. I solve for the rest of the unknowns now. The second row here gives me the solution x2 equals 0. And the first row here gives me the solution x1 equal 1/2 x3. That's right, from this line. Which in terms of t is 1/2 of t. If I put everything into a vector form, I end up with a description like this. This is a complete description of the null space of this matrix, and hence it's the complete description of the eigenvectors associated with this eigenvalue, lambda equal 1. You can make it look a bit nicer by just factoring 1/2, and then you end up with something like this. I put it in this form because originally, remember, my map, the analysis I have just done, you can do it on any matrix regardless of the nature of that matrix. But in this particular example, my matrix was the matrix of projection, and it looks like the eigenvector we come up with, it's exactly the eigenvector, it's exactly the vector, which was at the basis of my projection here map. Remember, B vector, that's the one. It's not a coincidental, it's a part of the nature of any projection map. Remember, here I just chose a random numerical example of a projection map, but in fact it's in nature of any projection map that the vector you're projecting on, it will be the eigenvector for the value 1. It is in nature of any projection map. Any questions? The analysis is not over yet because we just done half of it only, or in fact 1/3 of it if you measure by dimensions, if you measure by multiplicities. Altogether you have 3 multiplicities here. You just covered for 1 multiplicity only. You need to cover for the other 2 multiplicities. These are the multiplicities which are associated with the other eigenvalue, lambda equals 0. So we need to do that, we need to repeat the same analysis for the other eigenvalue. Here's my repetition. So I take my other eigenvalue, lambda equals 0. I start looking for the vectors which work like this. So I take my matrix A. I bring my matrix to the row echelon form. Again, I have pre-computed that. It's a row echelon form of my matrix. When you look at this row echelon form, you can see that you have 2 non-leading columns, which in terms of the eigenvectors means that this value has geometric this value has geometric multiplicity 2. It had algebraic multiplicity 2. It has geometric multiplicity 2. It's not always the case. Example we've done on Thursday before the break, we had an example where there was an eigenvalue with different multiplicities. It was algebraic multiplicity was 2, if I remember correctly, but the geometric multiplicity for the same eigenvalue was 1, if I remember correctly. So it's not always the case that geometric and algebraic multiplicities deliver the same value, but in this case it is the case. See, geometric is also 2 as the algebraic one. So now we need to find the null space. When you have a matrix with 2 non-leading columns, you need to parameterize each of them. So here's my parameterization. x3, I suggest we call it T. x2, my suggestion is to call it S. And all I need to do now, I need to solve for x1 from the only available non-zero row, from the first row. So my solution for x1 from the first row, it is like this, negative double T. And now I can present, this is a complete solution of my homogeneous system of linear equations. It's a complete description of the null space of this matrix. I will put this description now in vector form. Is a description in vector form. All coefficients in front of T, it's negative 2, no T in x2, and 1 in here, all of them here. And all coefficients in front of S, it's only 1 coefficient here, it's like this. That's a complete description of the null space in vector form. Or you can put it in the span way, like you can put it in the span language, you can put it like that. So the null space or the eigen subspace, that's another notation we introduced on Thursday before the break. The eigen subspace of the value 0 is span of these two vectors. Oh. Using the same language, I can tell now. Using the same language, I can tell now that the eigen subspace, which is associated with the value 1, is span of one vector B. And that's the end of the spectral analysis. It's a lengthy process which involves quite a few steps. And the danger in this process is that every next step relies on the careful and correct results of the step before. So you have to train yourself to do every step in the proper time and carefully and correctly. Otherwise, you will ruin every successive step. That's what we have tutorials for. That's what you have a yellow book for. But after a while, you will realize there isn't much to it. You just have to carefully follow this process. First, you identify the eigenvalues through characteristic polynomial. Then for each of the eigenvalue, you do this solution to a homogeneous system, and you describe this solution in vector form, and that is your eigen subspace, or that is your eigenvectors. I did it once on Thursday before the break. I've done it just again once over to remind you how we do this process. Any questions? Okay. If you don't have any questions, I would like to look even a bit deeper into projection maps from the point of view of spectral analysis. This will be a little bit more advanced analysis, but it's a nice, beautiful piece of the mathematics, and I'd like to share it with you. So, in fact, before I do that, I'll comment more on this slide. So, in this example, I showed you how to do the spectral analysis on a matrix, but as an example of matrix, I chose this matrix of projection map at the top of my slide here. At the top of my slide, I chose this matrix, which is a matrix of one of the projection maps, three-dimensional projection on this particularly chosen vector B, randomly chosen numerical vector B. We've done analysis, it's all fine, but while doing this analysis, we observed two interesting things. First of them is this, that the eigenvector which is associated with value 1 is exactly the vector B which was at the base of my projection. That's the first observation I did, and I told you this already, this is not coincidental, this is in the nature of projection maps. The second observation I'm about to do is this one. The second eigenvalue, 0 eigenvalue here, it had two linearly independent eigenvectors which span the whole eigen subspace, but interestingly enough, if I give a name to this vector C, if I call this vector D, just for brevity, if I call this to vector C and D, then interestingly enough, you can check that both of these two vectors, they are perpendicular to the first vector B. The vector B was, here it is, 1, 0, 2. If you test this with these two, you will realize they are perpendicular. I mean, if you test the dot product of these three vectors. That's another interesting thing, which is, again, not a coincidence. It's another nature of projection maps. What I would like to do on my next slide, I'd like to summarize these two observations as a formal statements, and I show you why they actually happens in the very generality. That will be an interesting insight both into projection maps and into spectral analysis. Any questions? I mean, before we start off with this, any questions? All right, so here we go. Here's my setting again, my projection map with the formula like this. It's just a formula which works for any projection map. Right. So we expect that the vector we're projecting upon is non-zero vector, otherwise it doesn't make sense to project anything, because if you use the zero vector in this formula, you will end up with a trivial zero map. You can do spectral analysis of a zero map, nobody can stop you, but the results will be trivial. It will be only one eigenvalue, zero eigenvalue, and the whole Rn will be the eigensubspace. So let's just, here we go. The observations we made on that particular example of a projection map, I summarized them in lemma, and there will be 3 parts in this lemma: A, B, and C. Here they are. First one says T always has 2 eigenvalues. There's no any exception to this. If you remember, eigenvalues, they are the solutions to characteristic polynomial, which is of degree n. In this setting, that will be of degree n. You can't do much about it. So in general, you may expect n different eigenvalues. In projection case, there always be 2, 0 and 1. So in this regard, projections, they are quite simple. It's only 2 eigenvalues, no matter how high your dimension is. The second one says the eigensubspace, which is associated with the first eigenvalue, with 1, is always one-dimensional, is always span of the B vector, which at the base of at the core of your projection. And the second one, the third part of the lemma says the eigensubspace, which is associated with the second eigenvalue, is perpendicular to the B vector. So any element here is perpendicular to B. These are the observations we made on my slide with my numerical example. I would like to just show you why this is true in very generality, and it's a nice piece of mathematics. In fact, it will bring up all of those linear dependence, linear independence arguments you love so much when we discuss with you vectors. Here we go. Proof. So here's how we're going to structure this proof. Look at this. I'm going to take a value. I'm going to take an eigenvalue and an eigenvector of my projection map. So let me just make the assumption that we have a x and lambda which connected like this. So that's when I call lambda eigenvalue and x is eigenvector. And I would like to study this relation now in the context of my projection map. Projection map, it has a particular formula, isn't it? I mean, we have a very direct, very concrete formula. So if I use this formula here in place of t of x, that will show me something. So here's my usage of that. I'm going to replace my left-hand side with the formula, this formula, for the projection map. Here it is. I just subbed in my formula for t of x on the left-hand side here, and that gives me some substance to study. In fact, what I will do is this. I will move everything on one side. So I mean, every term will be on the left-hand side, and there will be only zero vector on the right-hand side. That will be the expression of this type. That will be the expression of this type. And then I'm going to look at this from the point of view of linear combinational vectors, because in fact, if you look at this carefully, you'll see a combination of 2 vectors. One of them is vector b, the other one is vector x. This is a number. This is a number. It's a huge bracket, but still it's just one number. So my next step will be I will consider 2 different options. First option will be that these 2 vectors are linearly independent, and the second option will be that these 2 vectors are linearly dependent. It may happen either way, But one way or another, these two possibilities, they will cover, they are mutually disjoint possibilities. They will cover all different relations between B and X. They are either linearly dependent or linearly independent. There's no any other options for B and X to be. For vector B and vector X to be. So look at this. If they are linearly independent, then this relation, it is a linear combination of two. Excuse me. What's your name? The gentleman on the left-hand side with the yellow book in his hand. What's your name? I didn't catch that. So tell me, Alan. We have two vectors and linear combination of those two vectors, isn't it? Yes or no? Here, do you see a linear combination of two vectors here? Yes, you do. What are the vectors? Okay, so if you make the assumption that these two are linearly independent, what can we say about the coefficients? Which coefficients are going to be zero? Which coefficients are going to be zero? Good. Here's a good observation. So the first option tells me if B and X are linearly independent, then both of the coefficients must be zero, as we have a suggestion from the class right now. And that covers for the first option, because if lambda is zero, then that's the first option in my part one of the lemma. So because they are linearly independent, lambda is zero. And the second one, being zero, it's a fraction. The fraction is zero when when the only numerator is zero, and that's what it is. X dot product with B is zero. And that actually covers for half of A and C at the same time, because it shows you that in this case, my eigenvalue will inevitably be zero, like in here. And every eigenvector, X was the eigenvector from here, every eigenvector will be perpendicular to the vector B. What do you say, Al? Would you agree? Would you agree with the conclusion I just made? That if B and X are linearly independent, then the eigenvalue must be zero, and the eigenvector must be perpendicular to the vector B. Probably. So you said it yourself, right? I mean, like if they are linearly independent, this bracket must be zero. But the bracket is zero when the numerator is zero. But the numerator is a dot product of two vectors. And dot product is zero. It's a geometrical sign of vectors being perpendicular, isn't it? That is exactly what I said here. Lovely. Now we need to study the second option, when B and X are linearly dependent, and that hopefully will cover for the rest of the lemma. Now, for two vectors being linearly dependent, how would you geometrically interpret two vectors being linearly dependent? Alan, help me, please. When two vectors are linearly dependent, how geometrically this manifests itself? That's right, thank you very much. Geometrically, two vectors being linearly, thank you very much. Geometrically, two vectors being linearly dependent, it means that one is a linear scalar multiple of the other, or one is parallel to the other. We're going to say it like this. If they are linearly dependent, it means that there is a number such that one is a scalar multiple of the other. Well, if it is so easily structured, why not we just try it? I mean, my lambda here and my x, they are subject to this relation. If x has this extra structure, if we know this extra information about x, we can try this information right here and see what happens. Let's just try it. So I'm trying this extra information in this relation. Yeah, that's right. I just plug in my vector into the formula for t. This is the formula for the T map, and I use the right-hand side from here in place of x. But this is just a scalar. Dot product of b and b, it's a length of b squared. So this is just basically cancels, and you end up with this expression. You end up with this expression. This is 1, so you end up with mu b, which is x itself. So you see what happens if I make an assumption that x is a vector which is parallel to b, and I mean if x is a vector which is parallel to vector b, and if I try this in this relation, the only option for lambda is 1, you see? The coefficient here is 1. And that covers for the second option. Lambda equal 1. And I mean, the part b is here already. You see, the eigenvector is a scalar multiple of b. So all the complete eigen subspace of the value 1 is span of b. Any questions? Would you trust us, Alan? Yeah, thank you for helping. Any other questions? Okay. Basically, you're fully equipped now to do most of the questions in relation to spectral analysis in the yellow book. From now on, I'll show you a few shortcuts and some applications of this. The first shortcut I'd like to discuss with you, it's when it comes to matrices of size 2. That's right. I showed you a few examples already where I did the spectral analysis in full. It was, on both occasions, it was for matrices of size 3 times 3. In case you're dealing with a matrix of size 2 times 2, there are some quick tricks you can use to save some time, and I'll show you these tricks. What's the time? Yeah, we have enough time to see these tricks. Hopefully, we have enough time to see these tricks. Yeah, that's right. Yeah, that's the slide which I call spectral analysis of 2 times 2 matrices. That's right. So I can do it in a very generality. Let me just take a matrix of size 2 times 2. I have enough letters to label every entry in that matrix with no indices, A, B, C, D, that will be. A, B, C, D, that will be. So if I follow the regular steps, now I can call them regular, we've done it already 2 or 3 times. In my spectral analysis, if I'm after eigenvalues, then I need to build the characteristic polynomial, which is of this shape. It's identity of size 2. Or if I use my matrix A, B, C, D, it will be like this. Because it's a matrix of 2 times 2, it's a small matrix, we can present the look or the formula for this characteristic polynomial in terms of A, B, and C, and D explicitly. So here it is. If I go after characteristic polynomial, I compute my determinant, so I multiply this difference with this difference, and I subtract B times C, here it is. I do the expansion, it's lambda square, A plus D lambda, and here's the end of it. This is the absolute general look of characteristic polynomial for 2 times 2 matrix. And here's my interesting observations. It's always a polynomial of degree 2. It's the degree of a polynomial, it's the size of the matrix you study. The trick you can use in the future when you approach a 2 times 2 matrix where you need to do a spectral analysis is here. You can always expect that will be a polynomial of degree 2, and you can always predict your coefficients next to lambda and the free coefficient. The highest coefficient is 1 all the time. It's a unital polynomial. But the coefficient next to A is the observation. It's a sum of entries on the main diagonal, A plus D. And the coefficient which with no lambda, the free coefficient, it has such a formula. Do you recognize such a formula? What is it? It's a determinant of the original matrix. So the next time you do spectral analysis of a matrix 2 times 2 of size 2 times 2, you can say immediately that the characteristic polynomial will always be of this shape, where coefficient next to lambda, it's the sum of the elements on the diagonal. This is a sum which we named once. I introduced this notion, the notion of a trace of a matrix, sum of elements on the main diagonal. And the free coefficient, it's the determinant of that matrix. That's the first shortcut you can do when you approach matrices of size 2 times 2. You can just jump straight here by computing trace and the determinant from the matrix itself, avoiding all of these intermediate steps. The other interesting thing is when you did quadratic, next step will be solving this quadratic equation, because the unital quadratic equation, it is very often you will be able to guess the solutions, isn't it? Because you will say there will be two roots. Some of those roots will be exactly coefficient next to lambda with the opposite sign, so it will be trace. And the product of those roots will be determinant. This is something which we know by the name of Vieta, isn't it? Vieta's theorem tells you that the solutions to quadratic polynomial in sum deliver the second coefficient. In product, they deliver the free coefficient. So here's another shortcut for you. When you after eigenvalues of the 2 times 2 matrix, you can probably write up this relation straight away and try to guess the eigenvalues. If you can't guess them, you can go back to the equation. If you can't guess them, you can go back to the equation. But guessing is always good attempt, because it will save you a lot of time. Yeah, well, here lambda 1 and lambda 2 are eigenvalues of A. Here's a test. Oh, here's an example. It's a question number 7 in tutorial book, part C. The matrix there is this one, 3, 5, 0, negative 6. 3, 5, 0, negative 6. So what I will do, I will write up these relations straight away without any characteristic polynomial. Here it is. Sum of the eigenvalues, it must be trace, which is in this case negative 3. Product of the eigenvalues, it must be determinant, which is in this case it's negative 18. Take 0, it's negative 18. And here we are guessing, isn't it? Because for this pair of numbers, we can guess the values, isn't it? One of them will be negative 6, the other one will be 3. Here's your shortcut. One value is negative 6, the other one is 3. So half of the spectral analysis, when you after eigenvalues alone, for 2 times 2 matrices, most of the time it will be guessing work as soon as you made these 2 lines correctly. The second part, when you go after eigenvectors, you still need to do it in full, and here it is. So I need to do it for each of the eigenvalues separately. So if I take the first eigenvalue, I need to study this matrix, A plus 6i. I need to study this matrix with my choice of eigenvalue. When you use 6 here, yeah, it will be 9. 3 plus 6 is 9, 5, and 0 in here. So you need to find a vector which is in the null space of this matrix. Again, for 2 times 2 matrices, finding such a vector is not a hard thing. You can guess it again. You can guess the unknowns. You need to choose to make this equation 0. My guessing is negative 5 and 9 is a good choice. So my eigen subspace associated with the value negative 6 is the span of one vector, negative 5 and 6. The second eigenvalue, I just repeat the same steps. I write up this matrix. A take 3i this time. Here it is. A take 3i I2. That's the matrix which has such a structure, isn't it? If you subtract 3, you will vanish this 3. And yeah, that's right. So if you after the vector which vanishes such a matrix, non-zero solution to such a matrix, the solution is 1, 0. Again, it's a guessing. Most of the time, it's just a guessing on educated guessing work. And so the eigen subspace associated with the value 3 is a span of this vector 1, 0. Interestingly enough, that's something which I just realized. Interestingly enough, my eigenvalues, these eigenvalues, negative 6 and 3, they turns out to be the values on the diagonal. Negative 6 and 3, that's right. Again, it's not coincidental. Something like this we have observed before. If you on Thursday, before the break, I gave you this example of diagonal matrices, if you remember. It was my first example when we started discussing the eigenvalues and eigenvectors. Diagonal matrices were the matrices where this was always the case. Eigenvalues for the diagonal matrices, they're just diagonal entries of those matrices. If you think a little bit about what happens with the upper triangular matrices, that's a typical example of the upper triangular matrix, isn't it? It's the one which has zeros under the diagonal and anything else above, including the diagonal. Half of the analysis we've done for the diagonal will be applicable here as well. Eigenvalues for the upper triangular matrices will be entries on the diagonal. That's where you stop. You can't go further beyond that, because for the diagonal matrices, if you remember, I hope you will eventually, you will revisit that if you don't. For the diagonals, not only we could easily predict the eigenvalues, we can also easily predict the eigenvectors. In the upper triangular case, it's no longer the case. Only the eigenvalues can be easily predicted, diagonal entries. Eigenvectors, for those you need to do the complete study, like in here. Any questions? Time is up. Any questions, please? No? All right, then we're done today. Thank you very much. I'll see you in 2 days. Thank you.